documents, a simple thing you might do is find other documents that have sort of the same histogram distribution of words, and that's likely to be a matching document. Things are much more sophisticated now in terms of how that works, but the basic idea is that I've got these code words that represent, or these words that represent something about the semantics, and so a similarity in distribution tells me that maybe there's a good chance that it's a similar type of document. So we want to do this in computer vision. So that's notionally represented here. So I've got a bunch of different objects, and I compute my features over all of these different objects, and I come up with what's shown down here. And I think this slide originally is from Fei-Fei Li, I'm not sure. And all of these are all of my code words for all of my different objects, right? So I take all my objects, and it's kind of like if you take all the documents in a library in the United States, and if they're all in English, you took all of those documents together, all of the words would be the set of the words that span all of those documents, right? And in fact, there are many more documents than there are words. And in fact, if you think of important words, words that actually have a lot of meaning, there's way more documents than words. So given a collection of words, visual words, for every document, I can say how many of each word is in each document, and that's what these histograms are meant to represent, right? So, you know, the bicycle has got these little bicycle pieces in it, all right? And something that might kind of look like this, I don't know, maybe, you know, this brown part down here looks a little bit like that brown part down there, but the idea is that there's many more of the bicycle elements than there are of the violin elements. This is referred to as a bag of visual words for obvious reasons, and the idea is that you're describing the entire image just by the histogram or the collection of those words, and you want to do access the same way they did in the documents world. So one way of doing this is just compare that distribution to the distributions of the word of the images that you know, and you can do it as, say, like a scalar dot product, right? So this histogram, if you normalize it to 1, you can think of it as a normalized vector, and I compare, or unit vector, I can compare unit vectors, for example, by taking dot product and finding nearest neighbor. So that's illustrated here. So I have some example d sub j, and I've got some query q, and I want to compare them. And so here are my two histograms. So my histogram here is 1814. My histogram over here is 5110. So remember, it's the same set of words, right? We're just going to say for all the words in English, what's the histogram? For all the words in my collection, what's the histogram? And I'm just going to compare, say, a similarity. So here's one example of where I take the dot product between the D and Q, divide by the length, and that's essentially giving me a similarity between them. And this is just written out for I equal 1 to V, where the idea is that you have V number of words. And again, we didn't talk about exactly how you decided what V should be. That's sort of part of the art of doing this work. So that's essentially doing a nearest neighbor lookup, right? Given some input, nearest neighbor, all right? But when we did discriminative classification, we said, you know, nearest neighbor has some power, but it can be kind of expensive in terms of storage and access, and maybe there are better ways we can do things. And in fact, we talked about training classifiers. So we talked about boosting or SVM. So we can do that for this example too, right? I have a whole bunch of images of violins. I've got a whole bunch of images of people. I've got a whole bunch of images of planes. I take all those images together, I find all the visual words, right? That gives me a vocabulary. I can build a histogram for each of the objects, and you know, so I have a bunch of training data, so I got a bunch of histograms for planes, histograms for cars, histograms for faces, and what do? I just train a support vector machine to make the decision, you know, is this a person, a plane, a car, etc. And in fact, that's exactly what was done. This work comes from 2004. There was a database, still is a database, referred to as the Caltech 101. It was one of the original data sets of enough images, of enough object types to start to explore this notion of database access. And what they were doing was they trained exactly a linear SVM, we talked about those before, using a bag of words on vectors. And there were a couple of different classes, faces, airplanes, cars, motorbikes, etc. And what's being reported here is that for each of the actual faces, you know, out of, you know, the average percentage of time that it was the best rank was 94, 96, 90. So you can see that it's pretty good. And then the other thing that they report is the mean rank. So when I try to find, whether or not, when I show a plane and I say, well, do I think it's a plane? Do I think it's a face? Do I think it's a motorbike, etc.? What is the average ranking of the correct answer? And you can see the value is 1.0 something, meaning that it almost always got the answer right. But it was just an example of this bag of words approach that says, I don't know anything about parts. I don't know anything about structure. What I know about is images. And I take locations and images, and I find interesting points. I build some description. Give me a word-like collection of those descriptors, and then for any new image, try to find the descriptors that are present. And that's what's referred to as bag of words. So this concludes our little addendum to object recognition. And what it will do is it'll let me later talk about, well, actually, it'll let me later not talk about activity recognition being done the same way, where instead of doing it over just images, you do it over video. But code words are a very sort of standard approach in computer vision these days, and so it was important that you know about it. So I went and stole some new slides to make this just for you guys, so I hope you appreciate it. All right, welcome back to Computer Vision. Today we're going to do just a little bit on video. Today, and I guess next one will be we're only going to talk 2 of these lessons on video. One could do almost an entire class on computer vision as applied to video and the things that are different, but we're not going to do a lot of that. A lot of what you've learned can be applied, obviously, to each of the individual images, and some of what you've learned where they're essentially 2-dimensional operators, you can apply those same operators in 3 dimensions, or other ways of thinking about video, but we're only going to do a little. In fact, talking about the 3 dimensions, video we're going to think of as a 3-dimensional signal. Right? So video, as shown here, is I have this image XY, and as time moves forward, time could also go that way, the idea is that I've got this volume of data. And so a pixel inside a video is actually a function of X, Y, and T. Right? So sometimes you'll see me going like this for video, and I'm talking about X, Y, and T. That's the way I think of video, is I think of video as a volume of data. So let's talk a little bit about some basic computer vision in video. So one might be object detection. So suppose your goal, and we'll talk a little bit about this next time, is activity recognition, right? You want to recognize what's going on. So you're going to recognize the activity of objects, of people, etc., but there are these entities doing something. So you might have to find these entities. That is, what are the things in here that are moving, that are doing something, that I need to try to label what their activity is. Nominally or notionally, you can think of as my goal is to find the independently moving things that are in this video. So here I've labeled this thing called background subtraction, and it's just example. I mean, here we have a scene where there's some cars moving, and the idea would be, well, we'd like to be able to find all of these moving blobs, right? In this particular case, all these moving blobs are the moving objects. Generically, background subtraction is used a lot. It used to be that people thought that background subtraction was trivial, and then they thought it was hard, and then they stopped thinking about it at all. It's still, this notion of separating out the entities is still a fundamental research area in computer vision. We're going to talk about some simple stuff here. So the most straightforward background subtraction is where you have a static camera. So the camera is not moving, and the idea being that if nothing is changing in the scene, then nothing is moving there either, and there's nothing to do, so you should go home and get some rest. All right? Background subtraction, as sort of simple and overly simplistic as it is used a lot in commercial systems, traffic monitoring, where they're counting cars or monitoring other things going on, various human action recognition, where you have people coming by and you want to be able to say something about walking, running, whatever. Human-computer interaction, so people will build systems where humans interact with a big display, and to pull the humans out from the background, they have to remove the background somehow, and sort of object tracking in general. So sometimes there what you'll do is you'll compensate for the motion of the camera, so you'll move the whole image back as if you had the camera stationary, and then you do background subtraction on that. How do you do background subtraction? Not so complicated. You have to estimate the background. So at some time t, remember we're doing x image of x, y, and t. I have to estimate the background, and then I'm going to subtract that background for whatever the current frame is, and wherever the difference is big enough, I'm going to call that my foreground mask. Okay, and it's an absolute difference because the background could be brighter than the thing that's moving, or it could be darker. Here's an example, sort of notionally. So here again, same image, right? And this is my estimated background. We'll talk a little bit later about how you might get such a beautiful background. And the idea would be to take your current image, subtract off the background, take the absolute value, and anywhere that it's bigger than the threshold, just output that. All right? Fine. But of course, the question is, what's a good estimate of the background? There's a form of background subtraction, which isn't really background subtraction at all, and it's referred to as frame differencing. Frame differencing is exactly what you might think. I'm going to assume that the background is whatever was in the picture just before. Okay? I'm just going to compare the current image to the last image. All right? And background subtraction becomes then I of x, y, and t minus I of x, y, and t minus 1. And if that value is greater than some threshold, I'll output that as my foreground mask. Okay? So here again, two examples. So here's I of x, y, t. Here's this van here. The van has moved a little bit. Let's see, which one's easiest to see that something has actually changed? Oh, here. So you see that this car is moving forward that way, and it's now moved past this line, but at time t minus 1, it was even with that line. Same thing that this van is moving forward. In fact, pay attention to this white van there, okay? I'm going to subtract from this image that background image, and then I'm going to take a look at different thresholds, right? Even before we look at the results, you can just think a little bit about how well will this work. Well, clearly, this is going to depend upon sort of what the objects look like, how fast they're moving, what the frame rate is, the threshold. So, sometimes this is good, and then from the slides I took, it's usually not. Well, and this can be shown here, right? So if I take different thresholds, so here's threshold of 25, of 50, of 100, and you can see, for this illumination, I don't know, a threshold somewhere between 50 and 100 seems to be going pretty well. You remember that white van that I told you about? Okay, well, that's right there, okay? So you can see the front of the van, you can see the back of the van, but there's a big hole eaten out of the middle of the van. What happened there? Well, the top of the van was just white, right? Just plain white. So the van top's here, and then in the next frame it's moved there. So the part where the van was, and now you can see the road behind it, that's a difference. And the part that was road, or the windshield, and now the top of the van there, you can see that's a difference. But the middle of the top of that van is white, and if I move it, what does it stay? White, so I don't get much of a difference. Okay, so this is a problem with frame differencing, is that large areas, even as they can move relatively quickly, but if you have large, constant intensity areas, that's just not going to work very well. So what's a better idea? So an obvious better idea is just what's referred to as mean filtering. Mean is my background now, instead of just being the last frame, which seems really silly, is just going to be the average of the last n frames. That's what it says here. Right? My background at time t is just the average of the sum of n frames in the past. Okay? In which case, then my background, my mask is now, I take my current image, subtract off that mean, and then is it greater than a threshold? Notice we now have a new parameter, right? We now have this parameter n. We have to worry about how much do we average. So here's an example on the same scene of using n as n equal 10, all right? So it's average. Now you'll see it's kind of a weird thing, right? So this van that has, kind of blended in there, right, as it averages over different places, and my foreground mask looks kind of like this, all right? And so I'm getting this extension of the cars in a variety of ways, and it's not so great. And the reason that it's not so great is that the average isn't really the right thing, right? So averaging over all those vans is getting me this kind of weird thing, right? Now, of course, if I had averaged over 50, but then I'd have all these other cars coming through, the average is very sensitive to this. What you can think of is that the background is just sort of a constant value with maybe a little variation, and occasionally I get some random perturbation, right? Some random noise comes along. We've seen this before. Remember when we were doing noise filtering of images and we were using Gaussians, etc., and then we put in that like salt and pepper noise, and we said salt and pepper noise, the problem with it is every now and then you get this big spike in there.